Okay, welcome to this series of client-server lectures. Uh, so far, we have spoken about the communication between client and server. We talked about the inter-process communication last time. Today, I will speak explicitly about an example that you have already seen in the sessions, in the lab sessions, which is called the echo server. Okay. The echo server, what we mean by that is this is a client here, as you can see. Client send a message to the server, says, my name is Mohammed. The server will echo the message and respond with, my name is Mohammed. So in reality, the way this goes, let me take this a little bit down so you can see that clearly. Okay. What happens is like this. This is my client again. That's my server. So the client will put the message hello. So let me take now the message is hello rather than my name is Mohammed. I want to echo this hello. What exactly goes on? The client will take this hello, will put it in the out stream. This is the output stream. Remember that the output stream, as you have learned in the session, is the means to put a message in using the output stream to take this message and put it in the CS socket. So the client socket, which we call and here I represent that with one single port, although I have already spoken that this socket actually looks something like this. Okay. The socket, as I said, it looks something like this. So if these are my sockets, if you will. Let me line this up so fast. Align left. Okay, so these are my sockets, and usually this is my port. So this is my port, and the port usually is connected to one or more, depending on how many sockets I create. I create this socket and this socket, so there will be multiple sockets created on. So when I say the port, client socket port, actually I mean one of these sockets. Okay, that's just to make sure that we stay connected to the notion of a socket versus port. Anyway, so here is the client. The client writes the hello into out. Out goes into the client socket. Now, once it goes in the socket here, from this time on, let me introduce the following term for you. And actually, let me create a new slide. And I will call this the communication process using TCP. Okay, what I mean by this, you say write hello into out called variable. This is what I said by the IO or output stream. So you know how to do that already. Now, from the hello, we'll go into the socket. This is processing time. I will call it processor time. So this is the processor will take this data from the socket into the port. Hello, from the socket to the physical port. No. Now, from this time on, the TCP stack takes over. So from this time on, it's no longer my programming. It's the programming which has already been done at the OS level or at the communication level. This is called the TCP stack. What the TCP will do, it will take the word hello, take it from socket, which is the memory location, to physical port. So this is step number 1. So now the TCP will be responsible for allocating the socket to the physical port. And here I have to mention that there will be scheduling delay time, which means, what I mean by that scheduling delay time, I mean that by that if there are other clients trying to send message, then the TCP will arrange for a time for each client, which means راح يعطي دور لكل client بالدور ليجي دورك انت بعد delay time or waiting time بخليك تبعث المسج تاعك. So once this is done, okay, so the hello now goes into the socket. Now from the TCP will take the hello message. Now hello message, and will break it into packets, because this is how the TCP IP protocol works. It takes the hello message, it divides it into packets. Now for this simple word hello, it will be only one packet, and the packet is around 1 kilobit. It's not usually, you don't the hello now will not fill the entire packet, but nevertheless you will use one packet to transfer it. Usually each packet contains the message itself, which is the word hello, okay, of course in binary. So this hello will be probably, you have 1, 2, 3, 4, 5, assume it's about 40 bits, and it will use the headers, for which will include remote address, where am I sending the package, will include the remote port, where am I sending which port I am going to access. It will include also the local, or the sender, which is actually, let me call it the client IP address. When I said here the remote address, I will say, actually let me repeat that, server IP address, the client IP address, client port. That's for the return, in order for the server to be able to return the response to the client. So the TCP will take care of this. It will create a packet and this packet will have the message, will have the header, which has the IP addresses and the remote ports, and maybe some other security information which are not the subject of this course. So let me show one more slide for this, how this will be. So so let me call this or actually let me do it this way. So the TCP protocol will receive my message from the socket. This is socket. Will take the message called the hello, and TCP protocol will create packet. This is now I will mention in a second that if the message is more than hello, then it will be let me use this better notation. I'll call it create packet. Okay. So the TCP will create the packet. Range, align middle. Okay. So in the header here, I will have the server IP, server port. Actually, let me do it differently so we know exactly what we are. So assuming that the server IP address is 78.22.1.5 server port, assume it is 1025. Remember, 1025 is not reserved. Client port, let's say it is 212.34.4.76. Client port, let's say it is 1035. Okay, so if this is the case and of course the word hello. So the packet will look now, I will use the decimal numbers, but those should be in different, will be in binary. So let me use the dash as 00, well, dash dash, then 1025, then 212.34.4.76 dash dash 1035, and then dash dash hello dash dash, and then there will be some more bits here. This will be filling bits so that you can fill the you can fill the packet. So this is our packet. So the TCP create a packet. Now this packet has to be transferred over the physical line. Here is what I've said here. This is the line that goes from the client to the server. This is the line that comes back from the server to the client. This could be wireless, could be Bluetooth, could be wired. It can be anything. So here, let me visualize this. So this is my client now. Again, it's my client. And this is my port. On the client side. So the packet now is sitting no. So the TCP, which is actually sitting on the client, the TCP protocol is on the client side. So this is the TCP protocol is part of the software stack which sits on the client. It prepares the packet and puts it on the port. So now this packet is ready to go on the channel. This is our so this is my channel. Let me put it in yellow color, and it should come to the that's my server port. Okay, so this is port number from the client 1035, port number 1035. This is port number 1025, and this is the IP address the client is 212.34.4.76, and this is the IP address 78.22.1.5. Okay, so now what happens is that for this packet to go into the line now, which means to leave the port, okay, we said that the TCP is responsible as a stack to create the packet. Now also the TCP protocol would be responsible to do the transfer the packet from the port to the physical line. Physical line means could be Wi-Fi, could be Bluetooth, could be wire, could be anything. Okay. Now let's say, assume that we will using Ethernet. Now for the Ethernet, of course, it will the Ethernet protocol to transfer using Ethernet to transfer packet from port to physical line, which is now putting the packet here. Let's make it more visible. Okay, so I put the packet on the channel. For this packet to go on the channel, what happens is that this is called the data transmission, which means transfer packet of data from the port to the physical line using the Ethernet Okay, so this is the process now. See, the client uses of course, as I put it here earlier, I write hello into the out variable, which is this one right here. So going back to this, so now the hello goes into the out comes to the client socket port. The TCP IP will take it and put it as a packet. Now the hello will be transmitted to the physical line. This is called transmitting data transmission. Then it will proceed over the link here, whether it's the wireless or wired or the Bluetooth. It goes all the way to the server side socket. The data will be received as packet, will be received by this the server socket, and will be transferred from the line from here. So there is here Let me visualize it as put it in red. So this will be the actual transfer, and here let me put it this way. Okay. No, this way. Transfer data from link to server socket. Okay, so this process here, we're transferring the data from the link to the server socket, and similarly we transfer the data here from client socket to link. Okay, that's what I've done here. Now the question, I need to ask the question. Let me put a new slide here. Okay, oops. Let's change the layout. What are the time calculations here? The first time, and let me bring the slide here. Oops. Now I don't want that. And okay. In the process, what is the time involved? Let me see if I have the slide here. I think I do. I don't need this now. Okay. Okay. So I have write hello into out into the port, the socket into the physical link. Hello goes over the physical link. From the physical link go to the socket. From the socket goes to the N here. From the N goes back to the out. From the out, writing back the word hello into the server socket and then back to the client. So let's follow this procedure step by step. And this will be the subject of the next video. I already have enough here. Okay, let me continue what I have started last time in the series of the client server video lectures. Last time I was talking about the echo server, where the client will prepare a message called hello. It will take it through the TCP protocol, put it on the create a packet. The packet looks something like this. It's about 1 kilobit in size. That's the at least one packet. Then the packet will go from the using the Ethernet card from the port to the link. This is the yellow here is my link, my communication link, and the packet travels all the way to the next to the server where it will be received by the client, by the server socket, and the server socket will take it and will repeat the process. It will take the packet, put it through the input stream, and once it's in the input stream, it puts it back in the output stream so that it will echo it again to the socket server, and from the from the server socket to the link, and from the link to the client socket, and then to the input where it's read back as hello. So this is process, and I number these. Number one, you transfer hello into the from the client socket to the link, and 2 it will travel, 3 it will be read through the socket, 4 it will be taken from the input to the output, 5 back to the socket, 6 back to the link, 7 back to the input stream of the client. So this is how the whole process goes. Now, in some of the times involved, let me take this now, and this one I have the client will issue a request to connect. Let me do the request to connect first communication. Remember that before I can send the hello message in the echo server, I have to establish a connection, as you have learned by this uh, statement. This is Java statement socket client. I create a client of the type socket, so it's called the new socket, and I specify the address, the remote address or the server address as localhost, which means both clients and servers are on the local host, and I'm using port number 4450. Assumptions, this is my client here. Let me put it in bold so you could see it better. Okay, thick. And this is my server, also thick. And the distance between the client and the server is 1000 meters. Actually, I will change this from localhost to some IP address, because if I was doing it on the local host, it will not be 1000 meters, it will be same, it will be actually 0 distance. So the distance here is about 1 kilometer between the client and the server, مسافة 1000 متر. فبالتالي the server is not local host, it is at certain IP which I mentioned in my previous slide. This is my IP address, server IP. And the port number, as I said, was 1025. That was my example, so let me correct it here. So the client issues the time, which is this is a time T called request one. This is my T start, uh, going from the socket, my socket, to the socket of the server, saying a new socket IP address 450. Now this statement, once it's executed by the processor on the client side, it will call the IP address, the TCP protocol, and the TCP will create a packet for this request connection with a server at IP address 782215 at port number 1025, and this packet will go through this link. So this is a time T request one. I have the request goes through the line, comes all the way here. Now this time here, this one, and let me again make it thick. This here is the time to communicate. This is actually, look at this time. This is the time I started the request. This is the time the message was received at the server side. Okay. So the socket client, which is this is on the server side, equals server.accept. So when the server.accept is executed, this request will be accepted by the server. Now, time needed for the server to accept the incoming connection request from the client. This is called taccept. This is a time. Usually, taccept is very small. That's not really big. Okay. But however, if it's very large, if the time to accept this request is large, then the session might expire and I will not be able to respond to the client using this link here. Okay. Now again, in the return back, when the server accepts the connection, this is connection request accepted. Okay, let's yellow this guy. Connection request accepted, and the acceptance goes back through the link, and the client will receive the response to its request. So this whole path from this guy to this place where it's received, this small circle here, if I can get it, and then when the server is ready to send the request to connect, or the accepted connect at this point, and it reaches the client at this point. So this total time here, this total time that goes from here all the way here, okay, this is my connection time. That's the request to connect, accept to connect. That's what the first step in the echo server. Okay. So now, having said that, now let's go into more detail now. Now the server and the client are already connected like this. Now they are connected. Now I want to send the hello request. Let's see what's involved. On the client side, I get the socket client equal new socket, so I have already done that. Actually, no, let me do the time calculation here. I want to do the time calculation for this process. On the client side, first I create a port on the client side. Okay, so this is creation of the port. And that's when I say client side, client equal new socket. So this is my socket called client, and it's new. And I am going to talk to 78. So this is another server, it's another IP address, doesn't matter. So to do that, this is CPU time, no communication here. And let's say it takes 10 microseconds. This is very simple operation. It's not big deal. You know what a microsecond is. A second has 1 million microseconds. Usually it takes much less, but let's say it's this way. Now, I want to initiate a TCP IP session, which means now I want the TCP to handle this communication to 7856.32.05. And this is a TCP time plus some waiting to see if the TCP is ready for me. So there is some TCP, let's say that the processor spends 10 microseconds creating the session, and there is waiting time before the TCP actually responds to me and accepts my call. So in my system here, I say there is 0 time waiting. What does it mean? It means that no other client or server is waiting for TCP IP to do a connection. So I will say there is no waiting time. Now, once I am done with this, initiate a TCP. Let me put this in red. I am done with that. I want to initiate a request to connect message. Now, this message which I have just put here, in new socket, I said this is a request to connect. So I need to initiate that message. And again, this is a CPU time. It will cost me about 10 microseconds. Every time the CPU gets involved, I have to pay 10 microseconds. Now, I want to deliver the message request to connect over the network card. So this is the here. That's my Ethernet. It's already. I am now here at this red ball here. I want to transfer this message. This here. I want to put it to start doing it like this, putting it into the line, going through the Ethernet card. So this process here, I want to deliver the message request to connect, which has already been done as a packet. Actually, when I say initiate a request to connect message here, this includes forming a packet. So it's pure CPU time, which does not take too much time. Now, how do I calculate this time? This requires the card, the Wi-Fi card. Here is my assumption. The Ethernet card speed. Okay. I assume that I have an Ethernet card speed 10 megabits per second. Today there are no 10 megabits per second. The least you have is 100. But let's say I have 10 megabits per second. And the message size, this is a default message, 800 bits. That's for request to connect. Usually it doesn't take that much, but usually the TCP will pad the packet، يعني بيعبي الباكت bits زيادة to make it standard مشان يبعث 800 bits أو 1024 bits أو something like that. So the speed now, the time it takes to transmit 800 bits over 10 megabits per second. How do I calculate that? Let me put it here in a new slide. Let's say calculations. Time to transmit 80 800 bits over 10 megabits per second Ethernet card. So here I will say the message size divide by the speed, or actually this is time equal, and this will be given by, in our case it will be 800 bits divided by 10 million bits per second, 1 2 3 4 5 6, which is equal 8. I take 2 bits from each, so I will have out of the 7 5 1 2 3 4 5. So this is per second. This time is in second, because you divide, the speed is bits per second, and this is bits, so this is bits, and this is bits per seconds. So the time here will be in seconds. In order to do that by microseconds, I will multiply this by million, 3 4 5 times 1 million. That's because the million is 1 million microseconds. I want to convert this into million. So I have 5 zeros here and 6 zeros, so I have 8 times 10, which is equal 80 microseconds. That's how I got the 80 here. So it's 80 microseconds, the time it takes to transfer the data from this card here to put it on the link. Now, how long does it take to go over to the next link? Let's see. So I have a time here called the propagation time. So I have finished this guy. So let me color it with red. Now I need to transmit the message request to connect over the physical line, which is here. Oh. This message now, look at this. Now it is on the link. I am done. Now I need to take it all the way here until it reaches this guy. It reaches the door of this port. So this time we call it the propagation time. We call it the propagation time. The propagation time now, I say it's 3.33 microseconds. How do I know that? Well, here is how. My assumption was that the distance it will cross is 1,000 meters. Okay, so it is 1,000 meters. So it has to go from here all the way, this guy, 1,000 meter. It has to come to this place. Now, how long does it take? So here now, propagation time, T propagation. The T propagation, I think this so the time propagation is it's the time it takes the message to travel 1,000 meters over the physical link. Now this is, since I have a distance here, the formula time equals distance divide speed. However, the speed is given by speed of light because this is electronic, and the speed of light is, I guess you guys know it, it's equal to 300 million meters per second, or it's 300,000 kilometers per second. So I will use it in meters because my distance is in meters. So my time here, let's get this a little bit. So my T propagation, T pro equals 1000 divided by 300 millions, 1, 2, 3, 4, 5, 6, which is actually, if I take 3 zeros, it will be 1 divided by, I have here 8 zeros, so I will take out of the 8, 3, then I have 5 zeros, 3, 1, 2, 3, 4, 5. This is in seconds. So this is seconds. If I want to convert that into microseconds, which is equal to, multiply it by 1,000,000 microseconds, 300, 1, 2, 3, times 1. Now, the reason I am multiplying it by millions, I want to convert this number to microseconds. So I have 6 zeros on top, 5 zeros bottom. So I will have 10 divided by 3, which is equal 3.33 micro. So it takes 3.33 microseconds to cross this distance from here all the way here because I have 1000 meters. So now I have calculated the time. These are the CPU times 10, 10, 10, and 80 for transferring the message over Ethernet, 3.33 microseconds to for the message to arrive at the server port. Now, for the message, once it arrives at the server port here, okay, now it has to be transmitted over the port. This transmission over the port to get into the server, to come like this, it needs this, it has to be done by the Ethernet card on this side. So if the Ethernet card on this side is the same speed as this guy, which is 10 megabits per second, then it takes exactly the same time, 80 microseconds. It takes 80 microseconds to be received at the port. Just like the time it took to get from the socket into the link. Here it comes from the link into the socket, and to be read it takes 80 microseconds. So now to initiate accept message, because now to say I accept, I like this, so you need a CPU time 10 microseconds. We assume there is no waiting time for the TCP, so this is 0. In some cases I will ask you that there are 5 processes waiting, so you have to wait for them, so you need to calculate the waiting time. Now to get the message back, to deliver the message accept over the net, again you need 80 microseconds. See, going back to this guy, it takes 80 microseconds for the message to go from this red to the blue to the socket. Now all of this from here, the hello, the end, the out, all of this takes 10 microseconds. It's CPU time. Now, for the message to go back to the line from the socket to this line, you need one more 80 microseconds, okay? And then to transmit the accept to client, which is this guy, it has to travel 1,000 meters against 3.33 microseconds. And finally, at the other link, at the other side, once it comes to this, it reaches the client, then again, I need here, so actually, oops. So now there are 4 of these data transmission from the client to the link here, 80 microseconds. There is 80 microseconds here, 80 here, 80 here. So that's why you see this is one data transmission, second data transmission. That's when the message arrives at the server. That's when the server puts the message on the link, and that's when the client takes this one more time. So you have 4 of them. Okay. Now for the propagation delay, you have two propagation delays. Okay. So now, if I add these up, the time, it turns out to be 376.66 microseconds. These are all microseconds. Okay. So that's the total. Okay. Now I want to mention some things here. Let me put one more slide and then I will quit right here. Total calculation. As we calculated this time, okay, total time calculated, which is actually the we call it the turnaround time, equal, we calculated this to be 376.66 microseconds. Okay, now in TCP IP type of system, TCP IP system, the turnaround time must be less than the TCP session. What is a TCP session? TCP session is when the client issues a request to connect, the TCP opens a session with a certain duration. For example, let's say 100 milliseconds. So TCP says, okay, I give you 100 milliseconds. If you don't get a response from the server within this time, I will close the session. Which means if the response from the server comes back to the client after 100 milliseconds, it will not be accepted. So the turnaround time must be equal or less than 100 milliseconds. Now, in case, let me put one more slide here. Some cases for session expiration. For example, if the distance is too large, for example, 10,000 kilometers, which is equal to 10 million meters. Then the propagation delay, T propagation, will be equal to message size. Assume now that the message size, assume distance is too large. No. Then the time of propagation will be T propagation will equal to 10 million, 1, 2, 3, 4, 5, 6, divided by 300 million, 1, 2, 3, 4, 5, 6, which is equal, so I have here 8 zeros and 7 zeros, so it will be 1 divided by 30 seconds, which is equal to, in terms of microseconds, will be 1 divided by 30 times 1 million, which is equal to 100,000 divided by 3, which is equal how much? 100,000 by 3 microseconds, 33,000. It's almost 33,000 microseconds, which is equal to 33 milliseconds. So it takes 33 milliseconds if the client and the server is 10,000 kilometers away. Now assume that message size was, let's say, instead of 80 bits, assume it was 80,000 bits. So the data transmission time will equal to 80,000 divide by 10 millions, 1, 2, 3, 4, 5, 6, which is equal 80,000. No, this is not right. You take 4 and out of the 7, 4, so it's 8 over 1,000. Which is equal to, if you multiply this by a million, so it will be 8,000 microseconds. Which is equal to 8 milliseconds. Then the total time will be, remember I had 4 data transmissions, to 4 times 8 plus 2 propagation time delay, so it's 2 times 33, and I will ignore the other times in microseconds, they are not big deal, so I have 32 plus 66 milliseconds, which is 98 milliseconds. So this time, so this is a case very close. If the TCP IP session was 100 millisecond, then I will skip the expiration by 2 milliseconds. So if the, assume here, I want to do this assumption, assume TCP session equals 50 milliseconds, or let's say 90 milliseconds. So in this case, TCP session expires before accept message reaches client. Okay, so now, which means that the connection between client and server will fail. Here is an interesting issue, and I will close this lecture immediately after this. Assume that you are running the same application which I have just described, and you are trying to connect to a server about 10,000 kilometers away, let's say in the United States, and you have the message size of about the same configuration right here. And you test your system, everything works fine. You were able to connect, and then you communicate, and then you can get data from your server 10,000 kilometers away. Now, you take this system and you deploy it at another computer. You give it to your friend or to the organization that's requesting your system, and out of a sudden there is a failure. The system doesn't work. You always have this error exception that you are not aware of what's going on. And you try to test your system, everything works. Every time you put it back on your computer, it works. Every time you transfer it to my computer, it doesn't work. What's the deal here? Well, the deal is that your TCP session may be configured to be smaller than my TCP session on my computer. Therefore, the system runs on your computer but fails on mine. Why difference in TCP configuration? This is a very interesting problem that requires software engineers to resolve it because it's not a matter of development, it's not a matter of the code, whether it's correct or incorrect, whether there are faults or bugs. There are no bugs anywhere, but it's a difference in the configuration, so you have to be careful whenever you develop a client-server architecture. Okay, let me stop right here and we will continue this discussion